so that it is easier for you to get the concept when you get back with the book. So up to last class, we saw about the different locking techniques. There were basic two-phase locking, then conservative two-phase locking, strict two-phase locking, and rigorous two-phase locking. Okay, so which one is mostly used is strict two-phase locking. Fine. Basic two-phase locking is a normal concept based on which the rest of the locking techniques are designed. Then your conservative strict two-phase locking is a kind of not practically possible locking concept. So based on that, again, strict 2PL has come and rigorous 2PL has come. So these things we saw in the last class. In order to have a control among the data items between the different transactions in a schedule, you are using the two-phase locking. Okay. So that time we also saw that there is a possibility of deadlock in these cases. When you are locking a data item, then there is a possibility of deadlock. Since you are in fifth sem, you are having this operating system. Has this topic been covered yet? Deadlock in operating
Yes,
system.
sir. It is covered.
Okay, then it is the same concept here also in database. There it is with respect to a process. Two or more process, when they are waiting for each other to release the items or resource so that they can use, that may give rise to deadlock. So here also same thing. When two or more transactions are waiting for each other to release the lock on the required data item, then that may give rise to deadlock. For example, you see here T1 and T2, there are two transactions. T1 is having read lock on Y, then it is reading the item Y. Okay, T2 is having a read lock on X, then it is reading the item X. Then write lock is required on X by T1. That means T1 is requesting for a write lock on X, which is held by T2 in read mode. Okay, so unless and until this lock is released, write lock will not be granted to T1. Fine. Similarly, T2 is requiring write lock on Y, which T1 is holding in read mode. So this is holding Y requiring X. This is holding X requiring Y. So both the transactions are waiting for each other to release the respective items so that they can use. So this will continue up to say infinite time, because no one will release the items held by each other, so that it becomes a deadlock. So you can detect using a graph, that is a deadlock graph. There also in OS also this concept is there, to draw a graph so that it gets easily detected that whether there is a deadlock or not. If there is a cycle, there is a deadlock. So T1 is with requiring X, which is held by T2. See here, T1 is requiring X, which is held by T2. T2 is requiring Y, which is held by T1. So you got a cycle. So in this manner, you can detect that there is a possibility of deadlock between two transactions uh, when they are requiring the items held by each other. Fine. So how do you avoid this kind of issue? Because the normal concept is that deadlock will happen, then you will solve. That is not the normal concept. The normal concept is that you have to detect it previously before happening of deadlock. You have to avoid it. So deadlock avoidance is more required than deadlock removal. Okay, it should not go to that stage where deadlock is happening. You should detect it and eliminate it or avoid it previously. Fine. So deadlock avoidance has greater impact, which is more required. Okay. So there are some schemes or there are some techniques by which you can detect the deadlock will be there or not previous to it happens actually. Oh, sorry. Yashwant Kumar is not allowed. He will tell Yashwant Kumar to join again. Wrongly, I denied entry. Yeah. Okay. So there are some techniques using which you can handle this deadlock situation before it happens actually. So for that, you require a concept called timestamp. Have you ever noticed that whatever transactions you perform, be it a railway reservation, if you are booking a ticket, or if you are booking something, whatever you are doing a shopping complex transaction, they print a bill, or suppose you are doing a ATM transaction, whatever thing, you get a time, DD, MM, YY, then the seconds also, the what second the transaction initiated, what second the transaction finished, all those things are detailed, the mention in the bill, okay, or in the slip. So those are also recorded in the database, that this transaction started at this time, this transaction ended at this time, this transaction affected this that items that we also saw in the first class of transaction, that uh, which are the data items being modified, which are the what was the previous value before modifying, then what is the afterwards value, all those things are detailed, noticed, okay, are kept in the database. So in order to have this deadlock avoidance, you need to have a uh, data called transaction timestamp. Every transaction is having a timestamp, means at what time the timestamp may be different. Suppose there are many transactions possible in your database. So for a day, you are counting the transactions as T1, T2, T3, T4, T5, T6, like this. Okay. Or maybe suppose the transactions are maybe infinite for a day with respect to a particular vendor or something, then that is also given a timestamp of time value. Suppose this transaction, the transaction at 3 second 3 p.m. 2 minute 25th second. Okay, so timestamp may be differently assigned or given to a transaction that may be consisting of a time or any value or sequence of transactions T1, T2, T3, likewise. Okay, so that is represented by TS of T. So transaction is T, then its timestamp will be represented by TS of T. Okay, if a transaction is suppose say T1, that is starting before the transaction of T2, then normally you assign this part. TS T1 is less than TS T2. That means say this is having a timestamp 1. This is the first transaction. This is having a timestamp 2. So 1 is less than 2. Likewise, you have to remember that if a older transaction is there, its timestamp will be lesser than the newer transaction. Okay. So it may be with respect to time also. Suppose this transaction timestamp is at 3 p.m. 10 minute and 20 second. This transaction will be at 3 p.m. 15 minute and 25th second. So this is greater. So older transactions are having lesser timestamp than the younger transactions. Fine. Okay. Now you see there are two schemes based on this timestamp mechanism that prevent the deadlock. Those are called wet die and wound wait. These are the two schemes that are used for deadlock prevention: wet die and wound wait. So in this, what happens is that suppose there is a transaction Ti trying to lock an item X, but X is locked by some other transaction Tj with a conflicting lock. Conflicting lock means with a separate lock. Suppose this is requesting a read lock, this is having a write lock. So lock will not be, sorry, the access will not be granted. Or suppose this is having a write lock, this is issuing a read lock, so access will not be granted unless and until this lock is released. It cannot be granted. So read and write, write and read, write and write, those are conflicting lock. Read and read, they are shared lock. So suppose Ti is issuing a read lock, Tj is having a read lock on X, so it will be granted because these are the read and read are not conflicting locks. Whereas read and write, write and read, write and write are conflicting. So if transaction Ti is requesting a lock on an item X which is held in a conflicting lock with another transaction, then there is a possibility of deadlock because it has to wait. If another transaction is holding with a conflicting lock on one item which is requested by that transaction, then there's a possibility that both of them may go into deadlock. So using this technique, wait die and wound wait, you can avoid that. So what happens in wait die? If ts of ti is less than ts of pay, uh, be attentive in this particular part in today's class, mostly because uh, this is the last part where you have to pay sincere attention. Afterwards whatever is there is uh, very easier than these concepts. Okay, wherever you have doubt you can immediately ask. So I told that timestamp is a value given to a transaction which is lesser for an older transaction, greater for an younger transaction. Because suppose older transaction is coming previously, it is given a number 1. Younger transaction is coming afterwards, it is the second transaction, say, so it is given a number 2. So obviously 1 is less than 2. So in that sense, ts of ti is less than ts of tj, means ti is older than tj. Here it is written. Okay, any doubt at any point of time? I am going phase by phase, you tell me. If in wait die, if ts of ti is less than ts of tj, means ti is an older transaction than tj, then ti is allowed to wait. Fine, ti, that means the older transaction, is allowed to wait. Okay, or else otherwise means ti may be a younger transaction. In the first case ti is a older transaction. Or if ti is younger than tj, getting, if ti is younger than tj, that means here ti is the transaction which is requesting, tj is having a lock on the data item x, ti is requesting. So suppose, since I am older, put me in ti, since you are younger, put yourself in tj. Suppose you have hold an item in write lock. Okay, then I am coming, I am a older person, so I am requesting you that you release the data item so that I can use it. So a older transaction is requesting a younger transaction, but the younger transaction is having a write lock. I am requesting a read lock on the data item. So what will happen that I will be allowed to wait. That means in this case I will be allowed to wait. I have to wait until you finish the work and release the lock. Fine. If the case is reverse, that means suppose ti is younger, that means suppose uh, you are younger, I am older, and I am holding the lock. You are coming and you are requesting. Okay, then what happens is that you will be aborted. That means the younger transaction will be aborted, or it says that ti dies. Okay, in the first case, the older transaction is requesting, it is allowed to wait because it is older. But in the second case, when older transaction is holding the item, younger transaction is requesting, it will be directly aborted. Okay, whatever transaction operation it has performed, it will be all gone, it will be directly aborted, and it will be restarted later with the same timestamp. Okay, at a separate, at a suppose 10 units interval of time, it will be again restarted, given the same timestamp value. So here what happens? Wait, die, wait and die. In the first case, wait, second case, die. That means between a younger and older transaction, the case is best. If the younger transaction is holding, you can write it down also, because that may be confusing for you later. Or I will be giving this recording, no issue. You can see it. So if a younger transaction is holding a lock on a data item, a older transaction is requesting, then older transaction will be allowed to wait until the younger transaction is releasing the lock. Or in the second case, if older transaction is holding the lock on the data item, younger transaction is requesting the lock, then younger transaction will be dying, or it will be aborted without given any access to the data item. It will be again restarted after some different amount of time, given the same timestamp. Fine. This is the first mechanism in which there is no possibility of lock, because no one is waiting. Okay. Who is waiting? In the first part, the older transaction is waiting. Okay, because younger transaction is performing the operation and the older transaction is waiting, because the older transaction may have done its all other um, things, so it is waiting for a final data item or something like that. It is allowed to wait, but the younger transaction will not be allowed to wait, because younger transaction will require more um, data items further down the line. So there is a possibility of higher possibility of deadlock, so it will not be allowed to wait ever. It will be directly aborted. There is another technique called wound wait. Wound wait, in the same case, if ts of ti, there is the older transaction, um, if if tj, that means the younger transaction, is holding a lock, and a older transaction is requesting the lock on the data item, then abort tj. That means tj, that means the younger transaction, will be directly aborted. In the previous case, what happened? In the same case, when a older transaction was requesting, then older transaction was allowed to wait. But in this case, older transaction is not allowed to wait. It will be directly getting the data item, and the younger transaction will directly be aborted. There is no consideration. Okay, wound wait is more threatful than your wait die, because in the previous case, older transaction was waiting. In this case, older transaction is directly aborting the younger transaction. So younger transaction is wounded. Okay, it will be directly aborted and restarted later with the same timestamp. Otherwise, that means if ti is younger than tj, then ti is allowed to wait. That means if a younger transaction is requesting, then it is allowed to wait. In the previous case, older transaction was allowed to wait. In this case, younger transaction is allowed to wait. If older transaction is requesting the data item, it will be directly wounding or aborting the younger transaction. Fine, no doubt.
Yes.
Read it once. It is from the book only. This is the book Navathe. Read it once. If still you are having confusion, then you can get back. All of you just have a go through. Just have a read on this too. Fine. See here, in the wait die, an older transaction is allowed to wait for a younger transaction. Until younger transaction is completed, the older transaction will wait. Then in the won't wait, it is opposite. A younger transaction is allowed to wait for an older one. Okay. So, but if an older transaction is requesting an item, then directly the younger transaction will be preempted or it will be aborted. But in the first case, the younger transaction will be completed till the time older transaction will wait. Okay. So both the schemes end up aborting the younger of the two transactions. In the first case and second case, both cases, the younger transaction is aborted when a older transaction is requesting. Okay. Uh, there is another set of technique where you do not require the timestamp. Fine. So those are these are called no waiting and cautious waiting. So in the no waiting algorithm, um, if a transaction is not getting a lock, it is immediately aborted. That means if a older transaction is having a lock and a younger transaction is coming, it is requesting a lock on that item, then it will be immediately aborted without making it wait. It will be immediately aborted because once it starts waiting, means there is a possibility of deadlock. So without letting it wait, it will be directly aborted and then restarted after a particular amount of time without checking whether the deadlock may occur or not. It will be again tested at that point of time whether deadlock, whether it is released or not. If not released, then again it will be aborted. So you just restart and abort. If you are not getting the item, then abort. That is no waiting. There is no possibility of waiting. Then cautious waiting. Cautious waiting is a advanced form of the no waiting. No waiting is very lethal. That means it is not at all waiting for anything. It is directly aborting. But cautious waiting says that in order to reduce the number of aborts or restart, it led to access the possibilities whether I will be directly aborting or I can wait for some time. So it says that suppose that transaction Ti tries to lock an item X. Suppose transaction Ti is waiting for an data item X, is requiring an data item X, but is not able to do because X is locked by Tj. Then uh, Tj is if Tj is not blocked, that means if Ti is requesting Tj, okay, if Ti is requesting Tj that release the lock on X, then if Tj is not blocked, it is continuing the execution, then Ti is allowed to wait. Okay, that means it checks that if Tj is not blocked, then Ti is uh, allowed to wait. Otherwise, it will be aborted. That means if Tj is also blocked and this one is again requesting, Ti is again requesting, so there will be a sequence of blocks. So more deadlocks will occur. So if I am requesting you, you are holding a data item X, okay, and you are not in blocked mode, you are executing. So I will be waiting so that you can complete the execution and I will be getting the data item. But if I am requesting and you are also requesting someone else, you are also blocked, then I will be immediately aborted. Fine. So that is cautious waiting. That means I will be waiting, but with a particular caution that if another one is not waiting, then I cannot. If another one is not waiting, then I can wait. If another one also is waiting, and I am requesting him, then I am not allowed to wait. I will be aborted. Getting? So it is based on three different transactions or more than that. If Ti, Tj, Tk, suppose J is waiting for K, I is waiting for J, that will not be allowed. If J is not waiting for anyone, it is proceeding with the operations, then Ti is requesting Tj, In that case, Ti will be allowed to wait. Otherwise, not. Got? Okay. So deadlock detection can be done through that wait for graph. That graph that you saw is named as wait for graph. Fine. So that you know that how to draw the graph. If I is waiting for j, then I to j there will be a edge. There will be an edge. If j is waiting for I, there will be an edge from j to I. In this case, here one is T1 is waiting for T2 to release X. Then T2 is waiting for T1 to release Y. So both of them are waiting for each other, and the graph is like this. So it will be a deadlock. Okay. Uh, yeah. Timeouts. This is another way to deal with the deadlock. In this method, what happens is that if a transaction waits for a period longer than a system defined timeout, that means there will be a defined operating system will be defining a timeout limit, suppose 10 unit. So one transaction will wait for maximum 10 unit of time to get the lock on the required data item. If it is not getting, then it will be aborted. Okay, so again it will be started at some other point of time, but it does not depend upon whether it is younger or older, or another one is waiting or not. No, it will be directly matched with the time limit given by the operating system. If operating system says that one transaction can wait maximum for 10 minutes or 10 unit or 20 minutes, so a transaction will wait for that much amount of time. If within that the lock is granted, then fine, it will be continuing its execution. Otherwise it will be aborted. Okay. Starvation, anyone knows how it is starvation?
So
In
when
a,
a newcome
hmm? Hello, voice disconnected. Anyone else? What is starvation? Operating system. ऑपरेटिंग सिस्टम में नहीं पता, ये तो ऑलरेडी कवर हो गया होगा.
It's like similar, kind of similar to timeouts. Like if it cannot be waiting forever like that. Like
No,
the
in that
one that
case,
comes first, it will be given priority.
no. That the case is reverse. In the timeout case, there is a fixed amount of time for which the transaction will be waiting.
Oh,
But in
yes.
case of starvation, the transaction will be waiting forever. It will be never given the lock.
Oh,
That
oh,
means
yes,
that,
yes,
that
yes.
will be it will be happening because of this happens because of priority. Suppose a
Oh,
very low priority process is there. Okay, it is waiting for a resource to be available from another process. Okay, but suppose the process which for which it is waiting is having higher priority. So after it completes, it will release the lock. Then in the meantime, another transaction or process comes which is having yet higher priority than this one. So that will be granted the access. So this one which is waiting from beginning, because of its lower priority, it never get access to the resource. So it keeps waiting forever, so that it dies. Okay, so that is starvation. Starvation
so,
means it never gets being faded. So in
yes,
that,
but in the case when a lower priority one is given, it gets preempted, and then the higher priority transaction gets the resource like that.
yes, that is the case. But
Ah,
suppose it has been preempted, But after preemption also it will be granted the access after a certain amount of time. But
After the
suppose that
higher
certain amount
priority
of time never comes, because every time some more higher priority process comes in between and takes the resource,
yes, yes.
and it is waiting in the queue forever. So in order to avoid that, avoid the starvation, what is the technique? Operating system, what is the technique to avoid the starvation? The technique is you increase the priority of the process one by one. Suppose after one day the process will be having a higher priority, so that at a certain point of time it is having a very high priority to get the resource. Otherwise it will be having always having the low priority, it will never get the resource, it will die of starvation. So if you can increase the priority bit by bit at a particular amount of time, suppose after 10 minutes of waiting, the lower priority process will be having a bit more priority. Suppose it was the priority was 20, then after waiting for 10 minutes the priority will be 19, then after waiting for another 10 minutes the priority will be 18. So the priority, if it increases at a certain point of time, it will be having a higher priority than another process which is having suppose 23 priority. So this one will be getting the access. If you do not increase the priority at all, it will be stagnant, that means it will be fixed at a particular priority value, so it will never get the access. Suppose this is the last priority process, suppose you have only 20 process in your system and this is the 20th priority process, so it will never get the access because all the prioritized process are getting the access. So in order to deal with that, you have to increase the priority bit by bit. Okay, that is the way, that is the only way to avoid starvation. So same case here, uh, starvation is same as your thing, operating system. So you can increase the priority bit by bit so that it gets access to the data item at a certain point of time. Okay. Uh, 1 second. Okay. There is some for the timestamp ordering algorithm. Timestamp ordering algorithm means based on timestamp value, you can also order the processes, or sorry, the transactions, so that they are performed in a deadlock free manner. They are executed in a deadlock free manner. So the concurrency control can be also realized through this timestamp ordering algorithm. What is this timestamp ordering? For this, you need to have two different values. One is read timestamp of an item, write timestamp of an item. What do you mean by read timestamp? Read underscore ts of x and write underscore ts of x. If suppose there are three transactions, fine, t1, t2, t3. Suppose now t1 is reading the item x. So read timestamp of x will be 1 because t1 is reading it. Suppose at a point of time t2 is reading it. So x will be set to, read timestamp of x will be set to 2 because t2 is reading it. Okay, suppose t2's timestamp is 2, t1's timestamp is 1, t3's timestamp is 3. So whoever transaction is reading the item x, read timestamp of x will be timestamp of that transaction. Got? Any doubt? Again, I am repeating. Whichever transaction is reading the data item x, the read timestamp of x will be set to that particular transaction's timestamp. Let me explain this through. Suppose there are two transactions, T1, T2. Okay. In this, I am reading. At item X, she is reading it at item Y. Okay. She is writing at item X. She is reading that item Z. Fine. So every data item is having two things. One is read timestamp, another one is write timestamp. So for X, who is reading it now? T1 is reading it. So read timestamp of X will be 1, because say T1's timestamp is 1, T2's timestamp is 2. So those timestamps will be assigned to read timestamp of X, write timestamp of X. Okay, so who is reading X? That T1 is reading in this at clock cycle 1. Suppose this is clock cycle 1, this is clock cycle 2, this is clock cycle 3, this is clock cycle 4. So at times as clock cycle 1, only X is getting read by T1. So read timestamp of X will be 1. Fine. At clock cycle 2, this will be there because X is not yet read by anyone else. So Y, read timestamp of Y will be 2. Okay. Then at clock cycle 3, these things will be still there. Only write timestamp of X will be set to 1. Similarly, for Z, read timestamp will be set to 2. Got? So whoever transaction is reading, that will be set. Suppose in the meantime there comes another transaction 3. Okay. It is reading the data item X again. So at clock cycle 1, 2, 3, 4, 5, 6, at clock cycle 6, read timestamp of X will be set to 3. Write timestamp will still be with 1 because 1 has read it last. Whoever has read it or write it last, as for their timestamp, it will be set. Got? Or any doubt? If suppose at next clock cycle, T3 is reading Y. So read timestamp of Y will be set to 3. So it changes. Read timestamp of an item or write timestamp of an item changes as per the transactions who read or write on them. Got? The read timestamp of item X is the largest timestamp among all the timestamps of transactions that have successfully read item X. Largest because of the younger transaction. So whoever has read it last, as per their timestamp, it will be set. Write timestamp also same. Whoever has written it last, as per their timestamp, it will be assigned. So based on this two, this timestamp ordering is defined. So timestamp ordering is nothing but uh, the order should not be violated in case of this basic timestamp ordering. Order means whenever a transaction T is issuing a read or write operation, the basic TO algorithm compares the timestamp of this and write timestamp of this to ensure that the timestamp order of transaction execution is not violated. Yeah. Uh, that means if suppose your there are same the two transactions are there, T1 and T2. Suppose you are requesting a lock on X to read it. Okay. T1 is requesting a lock on X to read it. T2 is writing on it. Okay. T2 is writing on it. The request of the lock was before T2 wrote. Okay. So T2 should have wrote after T1 has read it. But suppose in the issuing of lock, it got delayed. T1 is trying to read a data item X, which is already written by T2, because X write timestamp is now 2, because T2 has already written it. Read timestamp of X is 1, because uh, no, read timestamp of X is also 2, because T2 has read it and written it. But prior to that, T1 had requested, but it was not granted. So now if it is reading, it will be reading a false value, because T2 has already written it. T2 came afterwards, it has got the access of X, it wrote into it. Now if T1 is allowed to read, it will be reading a wrong value. So that is not allowed. So in this case, if you compare the read and write timestamp of the variable X, then you can get to know that who has already written into it. If a younger transaction which came later has already written, and you are a older transaction who had requested before, then there is no use of reading it now. Okay. So there are more further techniques based on this. That means when to roll back or not. These things we'll see in the consecutive next class. That will be last uh, class on this control concurrency control part. I'll cover it at once. So today's class is about this introduction to the deadlock. How do you avoid that? Then what is the timestamp? How do you uh, prevent the deadlock from happening? Those things. So any doubt up to now in transaction, in entire transaction, because I told you to read, go through the uh, concepts from the beginning of transaction class. If anyone has any doubt, you can ask.
Sir, what kind of question will come from this? Theoretical definition types or some coding?
Theoretical questions will be rare this time. Theoretical questions will not be that much. You expect 90% of the question to be this solvable type. You have to solve. So in this case, schedule will be given. Then you have to write the serialized schedule, whether this can be serialized or not. If yes, then what type of, with which type of serial schedule. Then view serializability. Uh, then what else is there? This locking. Then lost update problem. Those things. You
Okay,
practice the problems that are given in assignments and quizzes. Those
okay.
will be helpful. Don't expect theoretical questions this time.
So when will we be having our exams?
That is the not yet decided. There is no idea yet. We are also clueless. We have to just complete the syllabus before that. As far as the syllabus is concerned, we have to complete it. So there is few part left. concurrency locking, these things are also almost complete. Only this two backup and error recovery is there. These things will complete shortly in 1-2 class. This indexing part you have to go through in that NPTEL lecture that I have given, that 3 or 4 lectures from there. Query optimization I will take one class. Then this thing is left. If still your exams are not conducted, then we will go through this TRC and DRC, tuple relation calculus and domain relation calculus. Actually, this requires Blackboard. Without Blackboard, it is difficult for me to write it and show the examples. That's why I have left it. Still, we'll try what we can do on this TRC and DRC. Rest all things we have uh, almost complete. Syllabus is almost complete. So we don't know when will be the exams. It will be decided by the authority. They will say probably in December, third week or second week. We don't know. Then again, with Viva or project or questions will be given. I will not take Viva. I will directly give the questions and you will submit the answers. That is more easier. Viva will be taken for the lab part. So prepare for Viva questions. That will be theoretical questions. So you can prepare for that in theory manner. What is normalization? What is primary key? How do you define a primary key? All those things. Okay. Okay then. For today, let me take the attendance.